NASA STEM Engagement and Educator Professional Development Collaborative logo. Welcome to NASA STEM EPDC Quick Bits Big Ideas in Science Content. NASA STEM Engagement and Educator Professional Development Collaborative provides NASA resources and STEM strategies for STEM engagement. In this series, we intend to reach educators, parents, and caregivers to quickly explain a specific big idea in STEM. We will introduce a NASA example of how this idea is applied in the real world, and finally, we will demonstrate step-by-step how to lead this activity at home or in the classroom with your students. You might invite your students to watch with you at that time. We invite you to join us as we learn more from our specialists. Let's get started.
Hello, my name is Sara Torres, and I am an education specialist at Ames Research Center in California. The science idea we will be exploring in this quick bit video is forces and motion. We will take a closer look and demonstrate Newton's second and third laws of motion. A force is a push or a pull that acts upon an object as a result of its interaction with another object. Forces result from interactions. Some forces result from contact interactions. Examples of contact forces are frictional, tensional, and applied forces. Yet other forces are a result of action at a distant interactions, which are gravitational, electrical, and magnetic forces. According to Newton, whenever objects A and B interact with each other, they exert forces upon each other. When you sit in your chair, your body exerts a downward force on the chair, and the chair exerts an upward force on your body. There are two forces resulting from this interaction, a force on the chair and a force on your body. These two forces are called action and reaction forces and are the subject of Newton's third law of motion. Newton's third law is, for every action, there is an equal and opposite reaction. This statement means that in every interaction, there is a pair of forces acting on the two interacting objects. The size of the forces on the first object equals the size of the force on the second object. The direction of the force on the first object is opposite to the direction of the force on the second object. Forces always come in pairs, equal and opposite action, reaction, force pairs. Examples of practical problems could include the impact of collisions between two cars, between a car and stationary objects, and between a meteor and a space vehicle. Newton's second law is the motion of an object is determined by the sum of the forces acting on it. If the total force on the object is not zero, its motion will change. In other words, the greater the mass of the object, the greater the force needed to achieve the same change in motion. For any given object, a larger force causes a larger change in motion. In practical problems, this also means the harder you roll a ball, the farther it'll go. Today's activity, titled Extronaut Parachute Challenge, is part of the Next Gen STEM Commercial Crew Program series of educator guides. The link to this activity will be provided at the end of this Quick Bits video. Vocabulary that is helpful with students' understanding during this activity is force, which is a push or a pull of an object. Motion is a change in the position. Velocity is the quickness of motion or action and the direction. In this example, this car is traveling 50 miles an hour north. Mass is a measure of the amount of matter in an object. And gravity. Gravity is the force that attracts a body toward the center of the earth, toward any physical body having mass. In this activity, we will follow the engineering design process to construct, test, and analyze a prototype. We will also investigate forces on a falling object and effect of a parachute. Like engineers, we will apply mathematics to solve real-life problems involving angles, graphing, and area. The NASA Commercial Crew Program has engineers and aerospace specialists that work closely with industry partners Boeing and SpaceX. The partnership approach allows NASA engineers insight into each company's development process while providing access to the agency's technical expertise and resources. Crew safety is paramount in the return of human spaceflight launches for NASA's Kennedy Space Center, and parachute testing provides valuable data to help each partner meet NASA's requirement for certification and safety. In today's STEM activity, the big idea is the greater the mass of the object, the greater the force needed to achieve the same change in motion. In today's activity, we will use an egg as our astronaut. What do you think will happen to the egg if we drop it from a second story or higher of a building? What forces are acting on the egg when it drops from a building? Why will the egg break or crack? Constraints are limitations on the design. These may be materials available, the cost of materials, or the amount of time that you have to develop the solution. In this activity, the constraints are that the egg must hit the ground or floor first. Nothing can be attached to the egg except the harness, and the egg must fall with a major or longer axis perpendicular to the ground. The materials you will need for this activity are string or ribbon for the suspension lines, tape, scissors, something to measure with such as a ruler, a plastic bag or tissue for the canopy, a plastic egg, and something to weigh the plastic egg down such as pennies or washers. Be sure to plan. It is always best to draw your diagram in your notebook or journal. This will enable you to follow your design in the creating stage. This will also help you to remember what works and what needs to be improved after testing. After you draw your design, draw a scale drawing of your canopy or the fabric part of your parachute. I'm using graph paper. If you don't have graph paper, there is one provided for you in the Extronaut Educator Guide. The link will be provided at the end of this video. If you don't have access to a printer, there are some pretty good videos online that show you how to make your own. This scale drawing is an estimation, since I don't have a compass, which is a tool that mathematicians and engineers use to draw an accurate circumference. In my example, the diameter is 50 centimeters, so D is equal to 50 centimeters. Now if you look at my cross section, it's not long enough to complete the 50 centimeters across in distance, so I'm going to use a scale factor. In this example, 1 square equals 5 centimeters. The diameter is constant all around the grid, so I need to start at the center, which is 0, 0. So I will count half the distance to the right, half the distance to the left, half the distance up, and half the distance down. Now remind your students that 1 square is equal to 5 centimeters. Mathematicians call this horizontal line across the page the x-axis. They also call this vertical line going up and down the y-axis. So now I will get to plotting. And remind your students again that 1 square equals 5 centimeters. I'm going to count and mark half the distance. We have 50 centimeters, and your students will calculate that half of 50 is 25. So I'm going to start counting half to the right, 5, 10, 15, 20, 25, and I will add my plot there. Half the distance to the left, 5, 10, 15, 20, 25. Half the distance up, 5, 10, 15, 20, 25. And half the distance down, 5, 10, 15, 20, 25. Now remind your students this is an estimation because I don't have a compass with me to make an accurate circumference. Now I will connect my dots, and this is the estimated surface area for my canopy. Now follow your diagram and begin to create. In the screen, string is being measured and cut at 30 centimeters. Tissue paper will be used to create the canopy. The tissue paper is folded into fourths and measured to 50 centimeters. Then scissors are being used to cut the excess tissue paper off. Next, the suspension lines are being secured to the tissue paper with Scotch tape. It's time to test. On the screen, the parachute is being released from a balcony. What force is acting on the plastic egg? You're right, gravity. Don't forget to write your results down in your notebook. After each test, add more pennies to increase the mass of the plastic egg and then test it out. Once you've collected all your data, it's time to make a graph. This graph is showing that as I increase the mass by adding more pennies to fill the inside of the plastic egg, the faster the egg falls to the floor. What do you think we will have to do to slow down the plastic egg with increased mass from falling so fast to the floor? So let's review the big idea. If the mass of the plastic egg increases, the faster the plastic egg falls to the floor, which means the greater the mass of the object, the greater the force needed to achieve the same change in motion. This is demonstrating Newton's second law. For more details, check out the Extronaut Parachute Challenge Educator Guide found at this website.
URL nasa.gov/STEM-ed-resources/extronaut-parachute-guide.html. Thanks for watching this NASA STEM EPDC Quick Bit. Don't forget to check out the description below for more information and links. www.txstate-epdc.net. Logos for the Texas State University LBJ Institute for STEM Education and Research, NASA STEM Engagement and Educator Professional Development Collaborative, and NASA Partner. The material contained in this document is based upon work supported by a National Aeronautics and Space Administration (NASA) grant or cooperative agreement. Any opinions, findings, conclusions, or recommendations expressed in this material are those of the author and do not necessarily reflect the views of NASA. Images and footage courtesy of NASA. Images and footage used under licenses from Shutterstock.com and Envato.